Good afternoon, everybody, and welcome back to your AP Physics 2 live stream. Today, we're discussing the loop rule and the junction rule, your favorite rules about circuits. As always, we'll start with a lesson overview, walk you through what you'll be learning today, and then we'll do our daily warm-up where we discussed yesterday's practice problem. Then we'll talk about what you need to know in order to be successful about circuits questions on the AP exam, work through some guided practice, some questions the College Board has maybe asked in the past. We'll do a debrief and summary, talk you through what we did today, and then leave you with an AP exam practice to work on for tomorrow's lesson. I am Joe Mancino from Glastonbury High School in Glastonbury, Connecticut.
And I'm Brendan Eaton from Reedy High School in Frisco, Texas. And Mr. Mancino's got some AP classroom updates for you.
I sure do. I don't know if you've noticed when you log into your AP classroom, but whether or not your teacher uses AP Classroom, even if you're enrolled as a test-only student, the College Board is giving you access to a whole bunch of online resources. So if you log into Classroom, you'll see a new optional student practice section that includes free response questions, and there's no special browser required. You don't have to use the lockdown browser. You'll find it as if it were an assignment from your teacher. Now, it's not an assignment. You don't have to do it. I'm not going to be grading it, but nice job. If you would like to do it, it is extra optional practice. What happened is that the course leads from the various AP courses chose questions that were already in the question bank that mirror or are representative of the sort of questions that you'll see when you take the AP test. So they went through the entire question bank and flagged some questions as, yeah, you know what, that is a really good fit for this year's exam. So the course leads did that and opened everything up to you. So if you would like some extra practice, not only for AP Physics, but for every other course that you're taking, you can log into Classroom right now, and those are available along with everything else that you need. So if you're already enrolled in a course section or you're registered for the exam, then you have access already immediately, even if you are, if your teacher is not using Classroom. So the questions were selected to help you prepare for this year's exam. These questions focus on the units that will be on this year's exam. You can, of course, answer the questions in any order. If you feel really confident with a bunch of Unit 1 stuff, well, focus more of your effort on the units where you need the most work. And you already have access to this content, so if you log in through AP Classroom, it is all right there for you, along with scoring guidelines and commentary. So please, please, please make use of that. A ton of work has gone into constructing really good tests specifically for this 2020 administration. So if you want some extra practice, that is a great place to find it. All right, now Mr. Eaton is going to take you through today's lesson overview. Through the course overview first.
Yeah, so let's do our course overview first. We've already taken care of fluids, thermo, and electrostatics, and we are currently right in the middle of circuits. So today, as you can see, is loop and junction rule. We still have capacitors and complex circuits to tackle before the end of the circuits review. After circuits, we'll dive into magnetism, which is my personal favorite unit, and that's where everything will basically just sum up for you. But as far as today is concerned, here's the lesson overview. We're going to start with Kirchhoff's loop rule, and specifically talking about the voltage drop around each loop. And we'll also discuss Kirchhoff's junction rule that states that current in has to equal the current out.
And here's what you should already know going into today. It's not a ton. We assume that you have seen schematic diagrams for common circuit elements. If you had to, you could probably draw a circuit already. We're not going to spend a ton of time practicing drawing circuits. The idea that some resistors follow Ohm's law, that is, they always have the same resistance, and some don't. Also, by now, I think you're really, really good at Ohm's law.
The skills that we will address today are using representations and models, making claims and predictions about natural phenomena, connecting concepts in and across domains, and applying mathematical routines.
So here it comes, the AP practiced question from yesterday. You had to design a lab to determine the resistivity of some material using a graph. You had a bunch of different cylinders of the material, you know, a voltmeter and an ammeter and some wires and a variable power source and a metric ruler. And you had to describe a procedure that you could use and the data that you would need to collect in order to make this graph, talk about the measurements to be taken and how you would set it up, um, and include a diagram of your setup. So if you drew a circuit that involved all of these things, that involved the variable power supply, that involved the ammeter, that involved the correctly connected voltmeter, that involved the rod, that was a really good start. Now, of course, this year you won't have to draw any circuit diagrams, but you may have to identify a circuit diagram that would be capable of answering a particular question in your diagram. We're hoping that if you didn't do it already, then by the end of today's lesson, you'll be able to describe how a voltmeter is used to compare electric potential at 2 points. We're hoping that by the end of today's lesson, if you didn't do it already, you're able to describe how an ammeter measures current through exactly 1 point in a circuit. And then the question is, how can the data be graphed in a way that is useful for determining the resistivity of the material? And how could the graph be analyzed to figure out what the resistivity even is? So there were a variety of ways that you could have done that. We left you with a clue at the end of yesterday's lesson. There's no way in all of this data to simply measure resistance. So you had to come up with some way to measure the resistance of the rod. R equals V divided by I is one of the rearrangements of Ohm's law that you probably used. And presumably you used the equation for resistance being resistivity times length divided by cross-sectional area and set those two things equal. So V over I equals resistivity times length divided by cross-sectional area, and arrange that in such a way that either the resistivity was the slope of the graph, or conceivably you could have done it so that resistivity was the y coordinate of all points on the graph, although that's a pretty uncommon way to do it, and it is doable. Okay, so this is a sketch of what we might have done. Your sketch may have looked different, but measure the potential difference across the rod with the voltmeter, measure the current with the ammeter, measure everything you can about the rod, and use one rod at a time with different potential differences. And then for the graph, do the graph that we talked about last class. You know, V over I compared to L over A, the slope should be the resistivity of the graph. All right, in the follow-up section of this, you have a big rectangular lump of this material, and the data below shows potential difference and the current through it. You had to sketch a plot that could be linearized to find the resistance of that one rod. Now remember, objects have resistance, materials have resistivity. In the first part of this question, you had several objects made of the same material. In this one, you have one object with its own resistance. So if you think about Ohm's law, it's V equals IR. So if you put V on the x-axis, voltage on the x-axis, potential difference on the x-axis, and potential difference on the y-axis and current on the x-axis, the slope of that graph, R equals V over I, the slope of that graph is R. And there you go. That was the practice problem from yesterday. Your goal is not going to be to design a lab on the AP Physics 2 exam, but it may be to explain and interpret a graph, to read a procedure or look over something that students did or a claim that they're making and evaluate that claim. One last piece of warm-up, because you may have to choose from a set of graphs and determine which graph represents a different situation. A positively charged particle is moving from the left to the right in this region between two parallel plates. There's a uniform electric field pointing from the top to the bottom. Which of those graphs could represent the particle's horizontal position as a function of time? Notice there are 4 graphs. Each graph has a different shape. The x-axis is always time, but the question is, which of these could be the horizontal position versus time? Well, there is no force accelerating that charge in the horizontal direction. It moves horizontally with constant velocity. So it would be a graph that has constant positive slope. But which of these could represent the vertical position as a function of time? Well, vertically, this thing enters that region with some value, some y-axis value, but the particle is slowly pushed downward with increasing speed because of the constant downward force. So we look for a graph that starts with no slope and has an increasingly negative slope. Which of those graphs could represent the particle's horizontal velocity as a function of time? Well, like I said, there's no force accelerating this thing in the horizontal direction. The horizontal velocity would be unaffected by the vertical electric field. So which of these graphs could show a constant horizontal velocity? It's that one on the top left. Finally, which of these could represent the vertical speed as a function of time? Now remember, speed, unlike velocity, is a scalar. It's not a vector. Well, what happens to the speed of this particle in the vertical direction? There is a constant force acting on a particle that just has its mass. Constant force divided by mass is going to be constant acceleration. This thing's going faster and faster over time.
All right, and here's what you need to know to be successful on this year's AP exam. So first off, we'll talk about Kirchhoff's loop rule and the fact that the total change in energy for a single bundle of charge as it makes around one loop is 0. And if there's multiple paths through a circuit, conservation of energy still applies to every single path. Conservation of energy just never leaves you, does it? Kirchhoff's junction rule. So wires connect at a junction. We'll point out junction several times to get used to saying that term and hearing that term. And through Kirchhoff's junction rule, the total current flowing into a junction has to equal the total current coming out of a junction. And lastly, we'll touch on power. Power is the rate at which electrical potential energy is converted into other forms of energy.
So throughout today's presentation, and very often on the AP Physics 2 exam, you'd see light bulbs, incandescent light bulbs, small incandescent light bulbs that can be powered by batteries. And my students say, Mancino, it's 2020. Why are we still talking about light bulbs? Can't we talk about something else? We talk about them because they're simple devices like springs or ramps or ideal gas pistons or beakers with a little hole at the bottom or pendulums. Those devices let us look at energy transformations without a lot of other complications. It's a really good device to look at. It's simple and straightforward. We can talk about what the energy is doing. We all know how to use the language. And you know a lot about light bulbs that makes talking about them uncomplicated. If the bulb is off, there's no current. If there's a bunch of identical bulbs, then the brightness indicates current. So if I say rank the brightness of these bulbs, we all sort of know what we're talking about. And the brightness indicates power. So rank the power output of these bulbs. Again, you're going to be thinking about brightness. And so that's why we talk about light bulbs, not because we think you're going to encounter a lot of incandescent light bulbs, but because they're a really good system to talk about. Now, I think it's quite likely that you have, in the past, built a simple circuit. It probably looked something like this. You attached a 1.5 volt battery to a light bulb in a stand with little screws that you tightened up, or maybe you just held the wires on there. And you probably noticed that the moment you connected that circuit up, the light bulb lit. But yesterday, we talked about drift velocity, and the fact that electron drift is on the order of 1 foot per hour. Now, I know that in my classroom, my wires are 14 inches long. That means it should take over an hour for a charge on one end of that wire to make it to the other end of that same wire. Yet it doesn't take an hour for the light bulb to light up. So I thought we would take a moment and talk about why that is. So give me just a moment to press that button and switch displays here. All right. Okay. So on your screen, you actually see the end of my presentation that I'm usually looking at. But what you see on the top, it says electron flow. So here in the circuit is an electron, one single charge. We're just grabbing an electron from anywhere in the wire. Remember, wires are already full of electrons when you buy them at the hardware store. There's no such thing as a wire that doesn't have electrons in it. The electrons are already in the wire to start with. So we're going to grab this electron, and once we've connected the battery to the circuit, the electron flows away from the negative end of the battery through the light bulb, through the curly filament in the light bulb, out the other end, and bumbles and wobbles along here. Now on my iPad here, this battery, this wire is almost a foot long, the entire circumference of this path. So this would really take an hour. And then some chemistry happens and some chemistry happens. And then another electron from somewhere else is going to move. But the point is, I could have started this electron's journey anywhere. We could have grabbed the electron that starts here. And done exactly the same path with it. The point is that as soon as the battery is connected, every electron that's already in the wire is going to start moving. This wire is already full of electrons. They're in the light bulb, they're in the wire, and they all start moving the moment that the battery is connected. There's already electrons there. They were already there in the beginning. Every electron starts moving at the same time. There's no, the electrons go here first and second or third. There is no first, second, or third. They all start moving together. But you may remember from class that we don't talk much about the flow of electrons. We talk about the positive flow of current. We always talk about current as if it moves like this, as if charges are moving out of the positive end of a battery through a light bulb and back through. There are historical reasons why we do that, although that's not really what's going on. So I have here a simple circuit drawn. Thanks again, FET. This simple circuit shows two things. I'm going to turn off any charges at all. It shows a battery connected to a light bulb, and the light bulb is on. We all know the light bulb is on because it's lit. And I can show the current and show the moving electrons in those wires. And what you'll notice is that these electrons are moving anti-clockwise. They're coming out of the negative end of the battery, going into the positive end, and that's what electrons really do. But because of historical accidents, we treat the flow of charge this way, as if they were positive charge carriers, bringing charge out the positive end of the battery. Mathematically, it works out the same. The amount of charge flowing past a point at any time, well, it's a negative times a negative anyway. So the math all works out the same way. But electrons are actually the things that are moving. I'm going to jump us back into the presentation right there. And this is a simple circuit, a battery connected to a light bulb. And I suspect that if you had to, you would diagram the circuit this way. Mr. Eaton, can you take us through the parts of this circuit diagram?
Sure. So the symbol that you see on the left-hand side, hopefully you're familiar with the fact that that's a symbol for a battery. That's something we thought you would know before you got into this. And the kind of squiggly line on the right-hand side, that's your resistor. So we know light bulbs are resistors. It's converting electric potential energy into light and heat. And we know that the battery is something that gives a charge electric potential energy. So a battery, when an electron is flowing through a battery, or positive charge, if we're using conventional current, when it goes to the battery gives that charge potential energy. So the battery causes a gain in potential energy. Once it flows through a resistor, once it passes through a resistor, the resistor causes that charge, or causes that electron to lose energy as it passes through. And we'll get into Kirchhoff's loop rule in just a second here. And you probably already know where we're going with this, but it's just a constant process of the battery making a charge gain potential and a resistor causing that charge to lose a potential energy. But throughout an entire loop, we know that the sum of the change in those potentials has to be equal to 0. In other words, the diagram that you just saw, if that was a 1.5 volt battery, that battery is giving 1 Coulomb of charge, 1.5 joules of energy. Therefore, if I know that the sum has to be 0, how much is lost? How much energy has to be lost across that resistor on the right-hand side? Well, it's still 1.5 joules per Coulomb of energy. Boom, boom.
Boom indeed.
So Kirchhoff's loop rule, here's the general statement of Kirchhoff's loop rule. As a charge goes around any complete loop inside of a circuit, the total increase in potential energy by the battery equals the total decrease in potential energy by the resistor. See how I added those words? Specifically because we want you to know exactly what those components inside the circuit are physically doing to a charge as the charge is moving throughout that circuit at 1 foot per hour. So all in all, this is still a statement of conservation of energy. We know energy up through the battery has to be equal to energy down through the resistor. So that's, again, why we call it a voltage drop across a resistor, because the resistor is causing the energy to be, it's actually using and dissipating energy of that charge in other forms. So that's the idea behind this. It says the amount of energy transferred to the resistors by the charge is equal to the amount transferred to the charges by the battery. Again, 1.5 joules per Coulomb up from the battery has to be 1.5 joules per Coulomb down. And we've got another diagram for you to take a look at.
So if charges moving through this battery are gaining energy, like it says 12 volts there. That means for every Coulomb of charge that goes through the battery, that Coulomb's worth of charge gains 12 volts, or every electron gains 12 electron volts. How much energy do they lose in the resistor? That is, what is the change in electric potential across the ends of that resistor? Well, in this simple circuit, a gain of 12 volts means the charges would lose either 12 electron volts per electron or 12 joules per Coulomb of charge. Now, things are about to get a little bit more complicated, but I think you're so good at the loop rule that you're going to nail this one. So same battery on the left, but now I have two unequal resistors on the right in that top resistor. Charges moving through that because of the properties of the resistor itself. Charges going through that resistor, every electron is losing 4 electron volts of energy, or every Coulomb is losing 4 joules. There's a 4 volt drop across that resistor. So what's the drop across the other resistor? If the total increase has to equal the total drop, well, it's 8 volts. Things get a little bit weirder. Probably the first time you encountered a diagram like this, you got worried, you didn't know what to do. Remember, the loop rule applies to individual loops. And there are 2 individual loops here, 2 different courses that a charge could take to begin and end at the same point. Physics teachers, if you're watching this, yeah, I see the third one too. So what you'll notice is that if we just consider one loop, that outer loop that involves the battery and the rightmost resistor, a 12 volt increase means a 12 volt drop. The loop rule has to work. For that inner loop, a 12 volt increase means a 12 volt drop. All we're doing is saying that regardless of which path charges go down, an individual charge, an individual electron is still going to lose 12 electron volts, regardless of which resistor that one electron goes through. One electron only goes through one path in a circuit. And regardless of the path that it goes to, it expends the energy that it takes to get through that resistor. So this would be the fully filled out voltage drop diagram for that circuit. So I'm going to give you this circuit. And let's take a look at what we've got. Well, the 12 volt battery is still there, but then there's that resistor right on the top of the diagram. And then I noticed charges can choose to go down the left fork and travel through a resistor where the potential difference is 5 volts, or travel through two resistors, one of which has a potential difference of 2 volts. So the question is, what is the voltage drop in that top resistor? If they need to add up to 12 volts, if the total increase equals the total drop, and all I know about in one path of this electron is that there's the 5-volt drop, well, I know that in the rest of that path, there must be a 7-volt drop. So for charges that through the battery, through that top resistor, through the 5-volt resistor, I know that that's a 12-volt drop. Well, what about that final resistor? For charges that maybe start in the 2-volt resistor, go through another resistor, gain 12 in the battery, and lose 12 electron volts. Sorry, and lose 7 electron volts through that top resistor. What's left to lose? Well, that's 3 volts. And another thing to notice is that for every loop in this circuit, the gain is 12 volts, the drop is 12 volts, but also for that cluster of the single resistor and then the 2 resistors in series, either way a charge moves, it still costs the same amount of energy to get through that section, regardless of the path.
Right, what this all means is that 1 volt is 1 joule per Coulomb of charge. That's the definition of a volt. And you'll also notice that Mr. Mancino was using electron volts. Well, that's how many volts each electron would lose as it passes through. So 12 volts means that every Coulomb of charge that passes through this circuit has 12 joules of energy to spend. And every time a whole Coulomb of charge passes through those resistors, the circuit transfers 12 joules of energy into other forms. And if those were light bulbs, they're transferring that energy into light, into heat, and maybe even sometimes a little bit of sound. But every time a whole Coulomb of charge moves through the battery gives that Coulomb of charge 12 joules of electric potential energy to then be used by those resistors again as it passes through the resistor in the circuit. It's just a constant process over and over again.
And notice, at no point did we mention the idea that batteries make charge, because they definitely don't. Remember, in the same way that fans don't make air. The charges don't start in the battery. There's no first bulb. There's no second bulb. The charges are already everywhere. So I'm going to leave you with this one. Looking at this, could you fill in all the missing voltages? Of course you could. Of course you could. In Kirchhoff's junction rule, it's important to know what a junction is. A junction is a point where 2 or more wires meet. If you take 2 wires with clips on the end and clip them together, you have made a junction. And if you take several wires and clip them together, you have made a junction. It doesn't need to be a whole bunch of wires. It just could be one wire meeting another wire, one wire meeting a resistor, 2 resistors meeting up. Regardless, a junction is where 2 or more conductors meet up. The junction rule says that the total current flowing into a junction equals the total current flowing out of that junction. It's conservation of matter. Remember, electrons are matter. They're small bits of matter, but they're matter. Every electron that goes in has to be accounted for. It comes out somewhere. So here's a wire carrying 10 amps of current. There's the wire, there's 10 amps. If we connect it to another wire, if we create a junction, what's the current in the other wire? Well, to follow the junction rule, if 10 amps goes in, 10 amps comes out. And there it is. That's the junction rule. It's never any more complicated than addition and subtraction. There's that same 10 amp wire, but what if it's split up 2 ways? Well, then the current splits up. Current travels, current moves, current flows. What if 7 amps of current is flowing in that top wire? What must be the current in the lower wire? Well, of course it's 3 amps. 10 went in. A total of 10 has to come out. All right, so we're going to put it all together. The loop rule, the junction rule, and V equals IR. So here's your question. Identical light bulbs, A and B, are connected in this circuit as shown. They're identical. How does the brightness of bulb A compare to the brightness of bulb B? Well, obviously, Mr. Mancino, you're thinking they're equally bright, and they're as bright as you are. Nice job. They would get the same current because whatever current is flowing through A flows through B. Those light bulbs are in series. Bulb B is in series with bulb A. They have the same current because there are no branches. Whatever current flows through A flows through B. So what would happen to the brightness of bulb A if I added bulb C right there? Well, what do you think would happen? Think it to yourself. You're maybe the only one in the room with yourself right now. Why don't you say it out loud? Good job. You're probably right. Or not. I don't know. Let's see what happens. There are 4 good ways to solve a scientific argument. We could put it up to a vote, but that's not how science works. We could ask an expert, but expertise doesn't really matter in science. We could hold it up to the model and see what happens. And ultimately, that's sort of what we're going to do. Although way number 4 is always the best to do it. Way number 4 is experiment. So we're going to turn back to the virtual lab at PhET. I have definitely verified this with my students in my classroom. Odds are good that you've done this in your classroom. But take a look at the circuit that I have set up. Same light bulbs, A, B, and C. The battery is in the same place. I see that C is connected, but there's definitely a switch there preventing current from flowing. So here it is. Here's that circuit just the way that I set it up. Bulbs A and B definitely have the same brightness. And you can sort of visually see that the current is equal in both of them. The rate of flow is equal in both of them. I'll even switch to conventional current so we can talk about clockwise current. I'm going to close the switch here and we'll see what the prediction, how the prediction bears out. Either bulb A will get brighter or dimmer or stay the same. So think about what you think is going to happen and focus on bulb A as I close the switch and put bulb C in parallel with bulb B. Bulb A, you'll be able to tell by the length of the brightness lines. Here it comes. Bulb A got brighter. I want you to watch the brightness of bulb B. Bulb B gets dimmer when I close that switch. So what's going on here? Bulbs B and C, once this switch is closed, bulbs B and C form their own parallel section in this circuit. The combined resistance of bulbs B and C is less than the resistance of bulb B. The combined resistance of B and C is now in series with bulb A, meaning that the entire resistance of this entire circuit, the resistance experienced by the battery, if batteries could feel anything, the battery would say, huh, the resistance went down. If the resistance goes down, the total current goes up. Now, you may have been thinking, well, nothing's changing bulb A, so the same current will go through bulb A. So bulb A will stay equally bright, and then the current will split in half at the BC junction. And you're right to an extent. You'll notice that the current through bulb A is double the current through bulbs B or C. However, we also need to think about the total resistance of the circuit. The total current goes up. All right, I'm going to switch back to the presentation. And I know that Mr. Eaton also has some circuits prepared to talk to you with. So I will wait for his say-so and see if he wants to switch right now. All right, we're going to switch this over to Mr. Eaton's screen. You go right ahead, Mr. Eaton.
Let's see if I can do this. I have faith. Okay, do you see a circuit? All right. Okay, so what I've built for you is just a basic series circuit with 2 light bulbs and 1 battery and a switch, just like you saw Mr. Mancino using. Oops, I accidentally closed the switch. Switch over to conventional current, just to be all politically correct here. All right. So when you close the switch, we notice that we have plenty of flow passing through both the light bulbs. And since they're identical light bulbs, they have identical brightness. And notice that the current is 0.45 amps. Okay, that's the current that's flowing just out of the right side of this bulb right here. I think you can see my cursor on the screen. I'm not sure if you can. All right, so one thing that students struggle with is knowing that the current in the series circuit is the same at all points. So I've got this little ammeter that can just detect current as it's passing through a wire. So if we place this right here, it says 0.45 amps, just like this little inline ammeter, like you normally connect an ammeter in series with the rest of your circuit, so on and so forth. Okay, I can move this around, and at every point, even inside the battery, it's showing that I've got 0.45 amps, which is awesome. So bam, bam, even through the light bulb, between the light bulbs, all that's good and dandy and fun and happy, okay? So we need to know that in series circuits, the current is the same through every single element at every single point inside of the circuit. So what I'm trying to say also is that wherever I put this little meter, it doesn't matter. I could have connected it right to the battery on this side. I could have put it next to the switch. I could have put it in between the light bulbs, and you would still experience the same current in every single point of that circuit. All right. Now you may know what happens to voltage inside of series circuits as well. This is a nice review. Okay, if I put this here, I want to know what voltage this battery has. Bam, that's apparently a 9-volt battery. All right. So we know that each Coulomb of charge gets 9 joules of energy, and you have to expend all those 9 joules of energy to get back to the other side of the battery in accordance with all of these nice little arrows moving in a clockwise fashion all the way back to the other side of the battery. All right. So if you have 2 identical bulbs, what's the voltage drop across every single bulb, knowing that my battery is a 9-volt battery? Well, we know the current's the same through both of them. And the voltage is also the same because they're identical bulbs. So I've got, actually, I flipped those around. No, they're not working if I do it that way. Oh, well. So I've got negative 4.5 volts. So I started with 9, and I've lost 4.5 volts across that first light bulb. How many volts do I have to lose across the right-hand light bulb? So I started with 9, lost 4.5. I have 4.5 joules per Coulomb left to travel through the second light bulb. So pretty good stuff here. All right, so that's a series circuit, identical bulbs, nothing too fancy. We open the switch. Remember, that's an open switch. This is a closed switch, open, close, open, right? And let's check out a parallel circuit really, really quickly.
One moment, Mr. Eden. Can you switch back to the previous tab? One thing that students might want to notice is that as charges travel through those bulbs, those charges are losing energy, but at no point are charges themselves getting used up. The ability of the battery to give the charges energy is getting used up. The chemical potential energy in the battery is slowly getting used up, but at no point are the charges themselves getting used up. When you build a circuit, it has a number of electrons, depending on the number and type of atoms in all the materials. When that circuit's done, it has the same number of charges. Carry on.
Good, it's good. Charges don't get tired. When switches are open, it's not because the charges they're tired so they can't jump over the bridge or anything like that. So interesting stuff. All right, so parallel circuit. I've got 3 light bulbs, 3 identical bulbs in a parallel circuit here. I've got a single battery again. And if I close one of these switches, okay, we know that this is a 9-volt battery. So what should the voltage drop across this one single light bulb be? You probably know that the loop rule says that it has to be 9 volts, and for whatever reason, my voltmeter is not working on this. It's defective. There we go. Okay, so voltage drop is 9 meters or 9 volts, which is exactly what we know to predict with Kirchhoff's loop rule. All right, so what happens when I close a second bulb? Close a second switch to make a parallel circuit with 2 bulbs. Okay, I want you to watch the ammeter showing current of 0.9 amps. And previously with Mr. Mancino's simulation, you know what happens when you add more bulbs in parallel. Does the current go up? Does the current go down? Let's close it. Current doubled. So I went from 0.9 amps to 1.8 amps. And let's predict what do you think that voltage drop is? That's a second loop. And notice those arrows are traveling this way, to the right-hand side of the ammeter. They don't go back up through that first bulb. They still travel back to the other side of the battery. So the voltage drop probably still needs to be exactly the same, 9 volts. So I have double the current, but the same voltage drop across each light bulb. All right, so let's close the third bulb. I think you know the pattern now. What happens to the current? Current is now triple what it was before. So it's 0.9 times 3. I have 3 bulbs in parallel. What's the voltage drop? Let's just prove it to you really quick. That's a third loop. So it still has to have the same voltage as the battery, which is 9 volts as well. So again, I think this is a situation where it's not you needing to calculate anything, it's understanding the concepts of those basic foundational principles inside of circuits that Kirchhoff's loop rule states that the voltage has to drop all the way back to 0 by the time it gets back to the other side of the battery, and the current in series stays constant. All right, and I'm going to unshare so we can go back to the presentation.
All righty.
All right, so last topic that we'll discuss before we see our practice questions at the end. Power. Power is just the rate at which energy is used. And the unit of power is watts. And I'm sure you've seen watts plenty of times before. Watts are what light bulbs are typically advertised as. Watts are even on every single electrical device that you use, because it's an indicator on how much energy is actually used. So 1 watt, 1 unit of power, is 1 joule of energy used every second. And one thing that I want to point out with watts is that you'll see it stated several different ways. Power is the rate at which the rate at which energy is consumed, the rate at which energy is converted, and it's also the rate at which work is done. That's the way you saw it in Physics 1. So on your formula chart for the AP exam, which you need to download and save to your computer and print it off and put it on your refrigerator, put it everywhere in your household, power is just I times delta V. Now, P equals IV is where we typically start, and we know that Ohm's law is V is equal to IR. I can substitute and rearrange power in a couple different formats, depending on what variables I'm given or what I'm trying to solve for. So power is also equal to I squared R, and power is also equal to V squared over R. I didn't show you the math on that, but it's super quick algebra just to substitute Ohm's law into the power equation.
So if power is current times voltage, that's one to think of, students use a variable resistor and a battery of known and constant EMF to obtain this graph. So they increase the resistance, which presumably decreases the current, and they measure the power converted by that resistor, and they measure the current through the resistor. What is the potential difference, the EMF, the terminal voltage of this ideal battery? Well, power is current times voltage. Power is current times the potential difference of the battery. There's power on the y-axis and current on the x-axis, meaning that the potential difference of this battery, the delta V of the battery, is the slope of this graph. The slope of this graph, well, we just look at that best fit line. The best fit line conveniently goes through 0, 0. So we can use 0, 0 and the 0.61 and say that that's about a 6-volt battery. Now, Mr. Eden, I saw you connecting that voltmeter in parallel with what you were measuring, and I saw your ammeter connected in series. Can you explain why you did that?
So I like to think of it as ammeters are counting the number of charges that are passing every second. So in order to count them, the charges actually need to flow through the ammeter. And in order to do that, you have to connect an ammeter in series with the rest of the circuit or the element that you're trying to figure out the current through in a different branch of a parallel circuit, but it still has to be connected in series with whatever you are trying to measure. But why have voltmeters connected in parallel is kind of interesting. Voltmeters are very high resistance, and I'm actually trying to connect a voltmeter in a manner that's not allowing charges to pass through the voltmeter. And we talked about electric potential and electric potential difference, delta V. That's what a voltmeter is actually measuring. A voltmeter has two probes on it, and it's physically looking at one side. If it were a thing that had thoughts and feelings, it's looking at one side and saying, what's the electric potential before the charge enters the light bulb? And use the other probe, what is the electric potential after it leaves that light bulb or resistor or whatever it is that you're trying to measure. So that's why we do that, is to make sure that the charges aren't actually passing through the voltmeter and expending energy through the voltmeter as well. So it's strictly just taking a temperature on one side and a temperature on the other and saying, hey, what's the energy? What's the energy? Compare the two, do the subtraction, and that's the delta V across the resistor. All right, and so here's your guided practice for today. We have 4 questions for you. The first one is about the junction rule. The second is about the brightness of light bulbs in different circuits. The third asks you to compare current within different bulbs in the same circuit. And the fourth uses Kirchhoff's loop rule. All right, here's your first one. This one uses the junction rule. So like we spoke about earlier, the junction rule just says that the current in has to be the current out. So the idea on this one is that a student connects this circuit and he measures the values for 3 currents. And he has a measurement error of plus or minus 0.2 amps. Can the information be used as evidence for the conservation of charge? And why or why not? So take a look at the currents coming out of the battery. Remember, the longer end of the battery is the positive side of the battery, and charge is flowing clockwise through this circuit. So the current coming out of the battery is 3.1 amps. What's coming back to the battery? So you would add 1.5 and 1.7 to figure out what's coming back to the battery. So my answer to this is yes. And I say because the sum of the currents in the 2 branches equals the current through the battery within the measurement error of plus or minus 0.2 amps. So 3.1 amps into the junction has to equal 1.5 out plus 1.7 out. So I know that that equals 3.2, but that's still within plus or minus 0.2 amps. And here's your second question. This is brightness of light bulbs in different circuits. So the figures below, you have 3 light bulbs. In which circuit will the bulbs have the exact same brightness? So I know Mr. Mancino had a awesome simulation earlier that looks exactly like the top right-hand corner diagram. And that one did not have all of the bulbs with the same brightness. They were identical bulbs, identical resistance, but they didn't have the same brightness. So I know in a series circuit, the current is the same through all the elements. So do you see a series circuit anywhere? Bottom right-hand corner is a good answer. If they have the same current, they're going to have the same brightness in this case. And what else do you think is going to, oh, that bottom left-hand one looks really similar to the top right-hand. I have 2 elements on one branch and 1 element or 1 bulb on the other branch. So I know that those can't have the same brightness. The parallel circuit in the top left-hand corner is another one that's going to have the bulbs all have the exact same brightness. All right, and here's your third question. It's about current. So the circuit above has 5 bulbs and they're connected to a battery. Which of the following are correct about the current in the circuit? So this one's a little tough. It's a little wordy. You have to look through and pick out little pieces that are different. For the sake of time, we're probably just going to jump right into, I'm moving all the way down to C. I like C because it says the current in bulb 1 is greater than the current in bulbs 2, 3, and 4. So why do I know that that needs to be true? Well, there's a junction there. And I know at a junction, some of the current's going to go up and around to bulb 2, and some of the current has to go through 3 and 4. And since that branch that has 3 and 4 has a higher resistance, less current will flow through 3 and 4 than it does through bulb 2. So the current in bulb 1 has to be greater than 2, 3, and 4 because the current that's feeding 2, 3, and 4 all has to come through 1. So it's kind of working backwards with junction rule and knowing that the current in has to be the current out of a junction. Now, the only other thing that looks really good here is option D. It says the currents in bulbs 1 and 5 are the same. Why do I know that's true? Well, junction rule still says that whatever's going into a junction is back out. So all the current has to flow through bulb 1 and all the current has to flow through bulb 5 to come back to the other side of the battery to get its certain number of joules per Coulomb of energy to then flow this through the circuit again.
All right, we're going to start our debrief and summary here and wrap up today's lesson. So the key takeaways from today are that resistors in series all have the same current since the charges move through one and then the other, that circuit elements in parallel have the same potential difference across them since charge moves through one or the other. And if there are multiple paths through a circuit, conservation of energy applies to each path. Wires connect at a junction. Total current flowing into a junction equals the total current flowing out. That power is the rate at which potential energy is converted into other forms of energy.
Can you answer why does current start flowing everywhere as soon as you connect a circuit?
So here comes your AP exam practice question. It's 2 quick screenshots, and then we'll reconvene tomorrow. Get a screenshot of this circuit and see if you can figure out the current that flows through that 40 ohm resistor. It's that one in the middle on the bottom. And then can you calculate the resistance of resistor R? Thank you so much for watching and taking this journey with us through circuits. We will see you again tomorrow with the answer to that question that we just left with.
Thanks again. We'll see you tomorrow.